All right, so you've done a bit of work involving anti-differentiation, and you've just done some work involving the idea of kinematics, where we go from the position to the velocity, speed, to the acceleration. Well, just as anti-differentiation can go from a differential equation to the original function, we can use anti-differentiation to go from velocity back to position, or acceleration back to velocity, or even better, acceleration back to velocity back to the position. And in a lot of cases, they will give you enough information that you can work out something's position. So let's look at an example. A body starts at the origin. It moves in a straight line. T is greater than 0. After t seconds, its velocity is v equals 5t minus 8. So I have a velocity equation, but I don't have anything else about the particle. I don't know where it is. I don't know how fast it's going. I just have that particular piece of information. So find position x in terms of t. So if I have a velocity equation and I want to get the position equation, I need to do something to the velocity equation. And that's going to be, I'm going to find the anti-differential. So in this case here, I'm going to anti-differentiate with respect to t. And that's going to get me back to the equation here. So I'm going to have 5t squared over 2 minus 8t plus c. Now, do you have enough information to figure out what that plus c is? And you actually do. Because what did I tell you at the start? A body starts at the origin. So when the time is 0, what is its position going to be? It is also going to be 0. That means that c equals 0, and we don't have to do anything else with it. We can just ignore it. We can drop it off. Hooray! If it was stated that it was starting in a particular position, then you would have to find out what c is, unfortunately. So the final answer, I don't know why it did that. So its final position x equals 5t squared over 2 minus 8t. find its position x when t equals 3. Well, I would substitute that into my position equation. So I'd find the perspective go. So put that into the position equation. T squared is 9, so that's 45 over 2 minus 24 over 1. X equals, it's negative 3 over 2. So in the context of the equation, of the original equation, where is it? Well, it is negative 1.5 centimeters to the left of O. Find the distance traveled in the first 3 seconds. So how far has it gone in the first 3 seconds? So we have to have a think about that. How far has it gone? Well, if it started at 0, so if it started there, when t equals 0, what is x? When t equals 0, x equals 0. When t equals 1, what is it? Well, when t equals 1, that's going to be 2.5 minus 8, negative 5.5. When t equals 2, when t equals 2, t equals 2, we've got 4, so that's going to be 10 minus 16, so that's going to be minus 6. But when t equals 3, we've already worked it out because we've got it up there. So what we need to do is we need to actually find what's happened. What's happened to our situation here? Because it looks as though it's changed. Rather odd. So it was 0, then it went really, really, really quickly to negative 5.5. Then it went only a little bit to 0.6. And then all of a sudden, it's right back here. It's changed direction and therefore changed its velocity. So, at some point, what speed did it have to be? If it was going to turn around and come back, how fast would it have to be going at some point to turn around? it would have to become 0. So what we need to do is we need to go back to our original velocity equation and find when v equals 0. V equals 0, so 0 equals 5t minus 8. 8 equals t over 5. So that is 1.6. So at t equals 1.6, its velocity was 0. So what we can do is go, well, okay, at t equals 1.6, what was its position? So we have our position equation here. 5t squared over 2 minus 8t at t equals 1.6, x equals question mark. All right, so we can bring up Mr. Calculator for this. There it is on the side. Clear all. So I'm just going to define it. F of x equals 5 x squared over 2 minus 8x. And then f of 1.6, negative 32 over 5. So that means that if you were modeling the particle, it went out and then back. And that turnaround point was at 1.6 seconds, which was negative 32 over 5, which will convert to a decimal, 6.4. So that's negative 6.4 to the left. So earlier, after 3 seconds, we worked out that it was 1.5 to the left. So it was 1.5 to the left. That means it went all the way out to 6.4 and then came all the way back to 1.5. So what was its average velocity? How far did it actually travel? So it went 6.4 to the left, and then it looks like it's turned around and come back. So how far is it between 6.4 and 1.5? Yeah. So the distance between 6.4 and 1.5 is 4.9. So the distance that it traveled is all of this. It went from here all the way to here and then back again. So the distance is equal to 6.4 centimeters plus 4.9. Which is 11.3 centimeters. But there's another word that goes in here. Displacement. Because the distance doesn't take into account directions it went. It only cares about the total cumulative distance that it traveled when going out and coming back and going out and coming back. In this case, the displacement cares about how far it's actually moved from where you started. And that is the statement I said before. 1.5 centimeters to the left of the origin is its displacement. So I've gone from a velocity equation to getting a position equation, using that position equation and the velocity equation to figure out the path of the particle by looking at how its velocity changed over time and noticing that because the velocity was linear, it means that its movement must have been parabolic, which means it would have gone out and come back. And then we've worked out how far it traveled and how far its final displacement was.